wide aspects of computer security and privacy. And the goal of the course is to get you up to speed on the state of the art in computer security. So what this means is that you're not expected to have any sort of background in computer security. If you do, that's great. But if not, all I expect is a basic undergraduate background in computer science, which means some background in operating systems, some background in architecture, some background in programming languages, and so on. And the hope is that through this course, you will get some exposure. In fact, it's going to be a breadth first exposure rather than a depth first exposure. I'll be covering a lot of topics to get you essentially up to speed in computer security, with the hope that with probably another 3 or 4 months worth of effort, you will be in a position where you can start contributing new material to the field. Okay, that's the idea. So there is not very much, as you will see, in terms of what you have to pick up. But once you pick an area, you can keep reading, and that process is expected to take around 3 to 4 months. Then you can start contributing new material to the field. So as you can imagine, this field is very, very dynamic, right? You continuously read incidents in the newspaper about things getting hacked all the time. So attacks continuously evolve, and defenses also continuously evolve. So what is new today will probably not be new 2 years down the line. Okay, so it is going to be considered routine. That is why this is a very exciting field, and that's why it's very important to keep up continuously with the methods that attackers develop and the methods that are developed to sort of defend against these kinds of attacks. So as a result, it should come as no surprise that any textbook is woefully out of date. Okay, so there is no good textbook in the field. There are some good references, of course, and I have made them available from the class website. Generally speaking, I like to make material available for free. So there is a free textbook that I have linked. It's a good reference that gives you an idea of the basic principles of the field. But because the field is so dynamic, we will be reading research papers. So the entire course is going to be based upon readings of research papers. Um, so if you have never read a research paper, I will also have something to say about that. So as I said, it's a very, very broad area. It's impossible to cover the entire breadth of computer security in a single course. Uh, we will be covering some system security issues in this course, and these are areas that are close to my own research. So I tend to focus on them. So I am going to be talking for nearly 1/3 of the semester on what are called memory errors and sandboxes. So these are probably the most widely exploited kind of security vulnerabilities. And for a while, and in fact, even now, they feature among the top 5 vulnerabilities worldwide. So we're going to learn about how these attacks are, so how these vulnerabilities come to be, how they are exploited by the bad guys, and how to defend against them. So that's the topic of sandboxes. Uh, we will then move on to the topic of web security, both web application as well as web browser security. And we will study what the major issues here are, what are the various kinds of ways in which web browsers as well as web applications can be attacked, and how to defend against them. And then we will move on to the topic of cloud computing, which is actually at this point around 10 to 15 years old, but continues to evolve rapidly. So cloud started off with the introduction of virtualization. So initial flavors of cloud computing started with what is called infrastructure as a service cloud computing, but that is long past. So now we have new and exciting forms of cloud computing, which are called microservices, serverless architectures, or function as a service. So we will be looking at some aspects of security in these kinds of cloud systems as well. And the course will conclude with a discussion of various kinds of IoT systems. So here it's impossible to cover the breadth, but we will be looking at some kinds of IoT systems. So for example, mobile devices that run Android. We will look at some topics on drones. We will look at some topics around smart homes, automated cars, and so on. What are the security issues there? So even for these topics, we will only be seeing the tip of the iceberg. So my goal here is to just give you an exposure and to start getting you thinking like a security person. Uh, if you really dig deep, you'll find that the realities here, they are vast. The issues are very deep and subtle. But my hope is to just get you started, right? It is to give you a taste of what computer security is, what computer security is all about, and what are the challenges that we face. what is there. So that you for that you will have to take a course by Bhavna, Arpita, Sanjit. In fact, now also Professor Chaya, she is there. I think Chaya and Arpita are offering a course together. So if you're interested in cryptography, you should consider that course as well. Okay, so reading research papers is going to be something that is new to most of you. It will not be, so the primary difference that you will see is that it's not written in a traditional textbook style. So when you read a textbook, it is written by a single author or by a small group of authors, which means that the textbook will have a consistent style across various chapters, and one chapter will follow the next. Research papers are not written that way, right? So research papers are written by individual groups around the world. So each paper will carry its own style, the style of the author that is writing the paper. So it's going to be a learning experience, right? So initially, when you start reading research papers, it takes around 3 to 4 hours to read a single paper, try to digest what that paper is trying to say, and appreciate the ideas that it presents. But you will soon get the hang of it, and you will find that this is a skill that you anyway need to pick up as part of your master's project. For example, all of you will be doing research projects, and it necessarily involves reading and understanding and, of course, extending research papers. Okay, so one of the side goals of this course is to try to teach you how to read research papers and to get to the core ideas of the papers, and to add these core ideas into a toolbox that you can carry with you moving forward. Right? So when you learn a course on algorithms, for example, right, you pick up certain tricks of the trade. You learn how to do things like divide and conquer, so on. So essentially, those are tools that you carry with you that you can use to solve problems, various kinds of problems. Essentially, the same kind of skill set is what I would like to impart. A certain set of tricks that you can carry with you that you can then use to solve security problems that you encounter in the field as you become software engineers yourself, and you will encounter security problems. It's inevitable that you will. Okay, so the general goal will be that you should try to read the paper that before coming to class. All the papers that we'll be using for the class are posted on the class webpage. Some of them have been linked from ACM or IEEE's website, which will require you to log in. But if you use your IISc VPN credentials, which I assume most of you must have got, the papers will be available for free through our institute library. Okay, so you may not understand everything, if that's okay in your first read. It's to just give you a general feel for the topic that the paper covers. And generally speaking, in class, we will discuss the context of the paper. I will tell you some anecdotes about the paper, how the paper came to be, as well as the technical material of the paper. And hopefully, with that understanding, if you read the paper again, it will be clearer. Okay, so you should try to read the paper twice or thrice in order to really get what it's trying to say. And I have made a selection of these papers. Most of these papers are essentially seminal research results of this field. Um, I will also choose some new papers that will give you a taste of the latest and greatest results in the field. What you should do as homework is that you should try to Google the name of the authors, the title of the paper, and so on. These are all big players in security, and you should just go and read about what these people are doing. And it's very interesting reading sometimes just to see the kind of creativity that exists in this field. And I hope to sort of convey some of that excitement to you throughout this semester. Okay, so what I will do now is I will just switch the presentation to the class webpage, and I will tell you about the weekly workload and what is expected, and also tell you about the various evaluation components and the grading criteria, which I'm sure many of you are eager to listen to. Okay, let me do that now. Okay, so here's the class webpage. Um, so one key detail is that this course timing is 11 to 12:30 p.m. Generally speaking, I am going to be available during this slot. And for the first couple of weeks, we will be doing this as a live lecture. So I will talk and we will make this a live session. I will be recording it and making it available via YouTube later on. But as the semester progresses, I may pre-record the lectures and put them on the class webpage before the class. And I will still be available in this Teams group during the class hours, and we can use this as a question and answer session. So it's up to you how you decide to use the time. You can see the lectures beforehand, or you can see them during the class hours. But I will be available for question answering during this time slot. I must also mention that these lectures are going to be publicly broadcast during the course of the semester, right? So IISc is the anchor institute for this government-led center called the Karnataka State Cybersecurity Center of Excellence, and we have agreed to offer this course for free through the center. So in case you're asking questions, as you are aware, I'm recording the lectures. Please be aware that your questions are going to be seen by an unknown audience, not just IISc as well. So you can please be aware. I just want to sensitize you to that fact. God knows how many people will be actually watching. We don't know. It's going to be available to all of the citizens of the state. So when you ask the questions, please be aware of the fact that your questions will also be broadcast to the entire citizens of the state and beyond, right? It's going to be on YouTube. Anybody can see it. So be aware of that fact when you're asking questions. You're welcome to ask. That's one thing that I encourage all my students to do. Please ask questions. No question is to be considered a stupid question. Please don't be shy about asking questions, because by asking questions is how you really learn the stuff. Okay, so that's that about the class webpage. Please take note of the URL. The most important thing, of course, the schedule. So you can see over here, I have posted the schedule for the entire semester. It's tentative, likely to change, but more or less I will try to stick to it. Most important, of course, are the dates of the exams that have been announced. First exam is on November 9th, second exam is on December 3rd, and the last exam, the final exam, is on January 20th. So these dates are fixed. Unfortunately, I will not have the flexibility to move them around. I know many of you will have exams and other courses. You might have interviews if your placement for your internships, whatever it is. You will have to work around these constraints. Unfortunately, that's the reality. In real life, you will have constraints that are often not going to move around, and unfortunately, these are going to be similar constraints. I'm not going to be able to move around the exam dates, so you will have to work around them. Of course, there are questions that you might have. What happens if my internet goes out? What happens if I fall ill, if I'm not able to take an exam? I'm more than accommodative here. I answer these questions in the FAQ section. Please go and take a look what essentially happens if you miss an exam. The short answer is that there'll be no compensatory exam. I'll just scale up the other components of the course for your grade. And if you miss the final exam, the idea is that I will not have a final exam, written final exam, but rather we will have an oral interview style exam of your to assess your knowledge of the stuff taught in the course. Okay, so that is the schedule. And let me tell you a few things that are coming up in the slides. The grading components. So there are going to be three major components, of course. There's going to be a homework, there's going to be 3 exams, and there's going to be a project. And you can see how they are essentially split up for the weightage of the course. So there are going to be two homeworks. The homeworks are available from the class webpage. You can do them as per your convenience. I will not be grading them. Okay. So these are more for your understanding and for you to develop a deeper understanding of what is being taught. But I will not be grading them. That said, you should do the homework. You should not ignore the homework thinking that they will not be graded, because there will be exam questions that you can only answer if you have done the homework. Okay. So you can be sure of that. There will be some questions which will require a detailed understanding of the difficulties that you face when you do the homework, and the exam will essentially test you on these difficulties. So by looking at the exam answers, I will know whether you have done the homework or not. So it is in your best interest to attempt the homework even though they are not graded. So there are 3 exams, as I said, worth 25%, 25%, and 35%. At this point, I have not decided exactly how the exams will be delivered. It might be a mix of objective style as well as written work. If it's objective style, it will be delivered through Teams, through a forms-based interface where you can go and click the correct answers. There might be short fields for you to write, long form answers as well. And this must be completed during the class hour. And if I decide that it's not going to be an objective style exam, it's going to be a written exam, then you'll be expected to write down the answers, scan the sheets, and then upload them. Okay, we'll figure out the modalities for all of these things. But basically speaking, exam 1 and exam 2 will just cover the relevant papers that are held just before exam 1 and just before exam 2. The final exam will be a cumulative exam, which means that all the papers that are read, that you will be reading in the course, are going to be considered fair game for the evaluation. Generally speaking, I just don't like rote learning kind of questions. So what I will be asking you is to apply your knowledge that you've learned in the papers. And generally speaking, what I will do is I'll combine the knowledge of multiple papers. So there might be questions that ask you to combine the ideas from multiple papers, and you should be ready for that. Okay. So that's the exam. And finally, there's a project which is worth 15% of your course grade, and I will get to that shortly. So this is going to be the grading criterion for the course, right? So you need to score at least 40 and above in order to pass the course. And generally speaking, every 10 points thereafter is going to be one grade bump. So I put this not to scare you, but rather to pacify you, because I find that many students are uncertain of their letter grade at any given point in the semester. You can be sure that based upon your current performance in the course, you can always calculate your own grade by looking at this table. Okay. So at the end of the semester, there is no confusion about what grade you've got, and you're well aware of your performance in the course, and you're the best judge of what grade you need in order to meet your placement criteria. Now, whatever it is, your GPA, your own personal ambitions as regarding your GPA, you will at any given point in the semester be able to calculate your performance in this course, including what grade you will get, by just looking at this table. Okay, so this table is essentially going to remain unchanged for the entire semester, and that's how we will be doing things. Okay, I will tell you about the project, and we'll come back about the policy on ethics in class. Okay. All right, so let me tell you about the project, and this is going to be a unique project this semester, unlike anything that I've offered before. So it's going to be a learning experience for you, it's going to be a learning experience for me. So the course project for this course is actually going to be a giant software engineering exercise involving the participation and coordination of everyone in class. Okay, so what we are going to do is that the entire class is going to work on one software system. I have not yet decided what the software system will be. It is, I will decide that based upon the number of students that finally register for the course. But most likely it's going to be mbed TLS, which is an SSL library that is really popular, and that's in wide use among in embedded systems. So this is an SSL library, which is essentially it's a library that is used for encryption and decryption. That's used to set up encrypted connections, and it's a library that is written in C. And the goal of this course is going to be to try to port the entire software system into a called Rust. So if you have never heard about Rust, it is probably the best language that you have never heard of. It is a memory safe language, and so essentially it's a language that is developed to prevent the kind of vulnerabilities that we're going to be talking about in the first few lectures of this course. So it's a language that prevents, that by design makes it very, very hard to have these kinds of security vulnerabilities. So number of companies today are taking extreme interest in this language. Facebook, Google, Amazon, all of these companies are essentially trying to rewrite large part of their software stacks at Rust, okay, because of the concrete benefits that it provides. It provides the runtime performance of C while providing the safety and the security features that a language like Java provides. So learning Rust is going to be a learning experience in itself, but all of you are going to try to coordinate to try to port as much of this mbed TLS library to Rust as possible. Now, I know that there are open source projects out there that are trying to do exactly the same thing, but that, of course, the goal is not to copy them. The goal is to try to understand the difficulties in doing this in a coordinated exercise in the entire class. So the nice thing about mbed TLS is that it's a very modular piece of software. One team can take one piece and then just work on it in isolation. Another team can take another piece and work on it in isolation. So the goal is that each one of you, right, you will be working in teams of 2 or teams of 1. You'll be working and trying to move this code to Rust and trying to understand the difficulties of doing so along the way. And at the end of the semester, all of you, of course, will be contributing to a GitHub repository where you'll all be contributing code. And I expect the software system to work at the end of the semester. Okay. So it's going to take a little bit of initiative from all of you to come up with the kinds of roles that exist in companies today. One of you will have to be a program manager, one of you will have to be a coordinator, and so on, that coordinates between the various teams in class, okay, and come up with the overall software system. Okay, so that is a project, and I will have more to say about the project as the semester goes. This is just to give you an overview. It is going to be a very coding intensive project. Last year, people did individual projects in Rust. This year, all of you are going to have to coordinate with the project on your own, together, the entire class. Okay, so that's the project. Let me go back to the grading. So we have a very strict no-nonsense cheating policy. As I said, the exams, of course, the exams are going to be open book, which means that you can consult whatever sources you have and then write the answers. What is forbidden, of course, is to discuss with the answers with your classmates over WhatsApp, over phone, or whatever. Given the online nature of teaching these days, very hard to do any sort of invigilation. So it's going to be, I'm going to have to trust you not to cheat on the exams. And of course, the project, as I said, there are efforts worldwide to try to port various software systems to Rust. Embed TLS is also one of them. I'm aware of at least 2 or 3 efforts. You should write your own code. You should not be taking code from other places. So we have a very strict no-nonsense policy on ethics in class. The DCC may have introduced you to this new policy that we have, and I am going to be adopting it. So if we find any instance of cheating in the course, both the cheater as well as the enabler will get an F in the course, and I will be sending an email via the department chair to the placement office to exclude you from all campus-related placement. Okay, no internship placement from the institute, no job-related placement from the institute. Okay, so your name and your ID will go to the placement office, and they will exclude you from all placement-related activity. So I know how seriously all of you take placement. So it is in your best interest to consider whether the benefits that you gain by cheating are going to be worth the cost. Okay, so that's the written sort of discussion of our ethics policy. All right. So let me just go back to the presentation, and I will shortly open up the floor for questions before I start any technical material. Okay. So we are back to the presentation. Okay. So as I said, I have been over the grading. So this is just what I already showed you in the class web page. I told you the exams are open book, and they're going to be they're going to be testing the deep understanding of material rather than just mere knowledge. Okay, so if you've just read the paper superficially, you will probably have a hard time in the exam. Okay, all right. I also told you about the project, right? I will have more to say. As I said, I would like to know how many people finally register for the course, and towards the end of October, I will be able to provide more clarity on exactly what subsystems of this embed TLS or any other software system I decide at that point, you will start working on. Okay. So generally speaking, I would expect you to start working probably early to mid-November and continuously work on the project till the end of the semester, okay, which is the end of January. So some details regarding the project, some yes answers. So yes, it is going to be difficult. It's going to have a ton of coding. There is going to be coordination required between teams, and that is going to be a big challenge. But that's the challenge that software engineers, millions of software engineers are facing right now as they are working from home and trying to, deliver their software projects. So we are going to mimic that experience. This is just preparation for the real world. It is going to take initiative from you to organize yourself into groups. You will have to create roles among yourself, program managers and whatnot, and coordinate software development. You'll have to decide upon APIs so as to ease the development and deliver the software at the end of the semester. And you are going to have to learn good software and engineering practices along the way. There is no single course that can teach you this. Only doing is going to be the best form of learning. Here are some no answers. Okay, so I will not give credit if your part is not working because somebody else failed to deliver theirs. Uh, in the real world, right? Either the entire team fails to ship the software, or they ship it, right? And if they don't ship, uh, of course, there are going to be consequences from the company. We are going to mimic that. Okay, I'm not going to be there to resolve conflicts between teams. You might not get along with your project partner, you might not get along with another team. uh, so you will have to resolve this among yourself. I'm not a KG teacher, right? So this is something that you will have to learn. You're all adults, you'll have to figure out how to resolve this. I'm also not here for overall coordination. That's your job as a class. You can figure out how to do the coordination. This Teams group, the chat window is always available. You can form your own Slack channel. You can form your own WhatsApp group. Whatever it is, you will have to form your own GitHub repositories, private as well as the common shared repository. I'm going to leave all of you to that to sort of figure out how to do it. And there'll be no extensions to the final deliverable because grades are due. Uh, and finally, the big no is that what you heard from your seniors last year is not going to help you this year, okay? Because the project is different. So you can take all what they told you and toss it out because your experience is going to be different from their experience. Okay, so as I said, right, I mean, I'll be recording lectures. Lectures are going to be available. Many of you, right, might have issues during the semester, internet issues, health issues, whatever. That's why, I'm not going to make attendance mandatory. I'm going to make all the lectures available via YouTube from the class webpage. There'll be a link. But you are encouraged to go and see this material because every class I will also cover material that is not in the paper, okay, and not in the slides, and not in any textbook. And the exams may actually contain questions based on this material. So it's in your best interest to come and attend the class, and listen to the material that's being covered in the lectures. Okay, so there's a certain discipline that I expect from people. Class starts at 11 o'clock, not 11:10 or 11:15. So if you're coming to the Teams meeting, please come at the sharp time. I am very punctual. I usually am there exactly on time, and I expect this from my students as well, right? So coming to class late is not acceptable. Of course, you may have power issues, you may have internet issues, and I will understand that. Okay, so you can feel free to write email to me during the semester. So please attend and ask questions in class. Be curious. Okay, so don't be scared to ask questions. Uh, I'm learning the subject as much as you are, right? I just have probably a 15 or 16-year head start over you, but I'm as much a student as you guys. So please feel free to ask questions. It is in the process of answering your questions that sometimes I learn the subtleties of the field myself. Believe it or not, right? 15 years down the line, I still have a lot to learn, and I would like to use the curiosity and the questions that you have to enhance my own knowledge and also give that knowledge to you. So please ask questions. I will never penalize you for asking questions. Uh, and as I said, some classes will be held live and some I will pre-record, but I will be available during class hours except for the 3 or 4 dates on which I will not be available, and I have already made those dates known to you via the class webpage. So 2 of them are institute holidays, and I have a personal commitment on one. On those days, I will not be available at the Teams meeting, but otherwise I will be. Okay, so that's the end of the administrative stuff. So let me just quickly stop sharing the slides and open the floor for questions. Please feel free to raise your hand via the Teams hand raise feature. I'm open to answering any questions that you may have about the logistical aspects of the course. Yes, Ashish, please go ahead.
Uh, are we supposed to learn Rust coding from now itself?
You are free to learn whenever you want to learn, right? I mean, I'm not going to give you a timetable and say start learning today. Uh, how does learning happen in the real world, right? I mean, if let's say you go and join a company, let's say you're not familiar with Python, but they ask you to do Python coding. They don't give you a timeline to learn Python, right? So it's up to you. You can start learning Rust from today. You can learn it once the project starts. It's up to you. I won't, as I said, there is going to be no spoon feeding in this course. I'm going to expect you all to be adults and form your own schedule.
Okay, apart from Rust, are we supposed to learn anything else or any tool or?
Well, you will be learning some stuff for the homework. You are required to learn some assembly language programming. You are required to learn how to use GDB and so on. My answer generally is that you'll have to pick up the tools of the trade as you go, because computer security is a very wide field. I cannot just say learn that and you have all the skills. You'll have to learn things as and when you encounter them. And I cannot just give you like a comprehensive list of things to learn right now. Uh, as you sort of feel the need, you will have to learn these things as you go.
Okay, thank
Okay?
you.
Yeah. Gokulnath?
Sir, there is no due date for the homework. So are we supposed to submit it, or is it for our own doing itself?
As I said, I'm not going to grade it, so there's going to be no due date. You are free to do it, you're free not to do it, but there will be questions in the exam based upon the homework, based upon. So the questions in the exam will test deep understanding that you can only gain if you do the homework yourself. So while I will not be setting any due dates for the homework, I do expect you to have completed them before the exams. So homework one before exam one and homework two before exam two.
Okay, thank you, Professor.
Yeah. Any further questions? Please feel free to raise your hand. I will call upon you. Yes, Manu.
Okay, sir, in the syllabus and reading section, they mentioned some papers, required readings. So whether this entire semester is based on these papers, or whether we want to refer some other papers related to this.
So I will be covering these papers in class, but of course, if you are interested in reading more, I can always provide you pointers. The best way, of course, is when you read a paper, the paper will have references. You should go and read those references recursively, right? Uh, that is the best way to sort of develop depth in the field. So if you're interested in what one particular paper has to say, for instance, you can just go, sort of depth first, reading the references and so on. And so you can essentially become an expert in that sub area. But I will, in this course, be covering the papers that have been pointed to in the class webpage, which are supposed to give you like a breadth first overview of some popular areas in computer security.
Okay.
Yeah.
So actually, I don't have any previous experience on this security area or cryptography. So
Right.
before reading these papers, is there any prerequisite textbooks or something that I have to read or?
No, so I will only assume a basic undergraduate exposure to computer science, which
Okay.
means some operating systems experience, some computer architecture experience, some programming languages experience, and so on. And you will have to pick things up as you go. So if it gives you any sort of comfort so I teach computer security, but uh, I have never taken a computer security course myself, in the sense that I've never been a student in a computer security course myself. Everything that I know about computer security, I picked up by reading papers over the course of the years. So if that gives you some sort of confidence or comfort, that that's an anecdotal experience. Okay.
Okay.
So I don't expect you to have any prior experience yourself.
Okay. Thank
Yeah.
you, sir. Thank you.
Yeah. Yeah. Okay. So Manu, you can probably switch off the raise hand, otherwise I'll get confused. Yeah. Any further questions? Okay. So yes, Sakya. Please go ahead, Sakya. I think you're on mute.
Yes, sir. I'm not able to access the chat window. So how to if they have to join somewhere else to access the chat window?
I think it should be available from Teams. I'm not the expert here. Does anybody else in class want to chime in? I think that from Teams you should be able to access the chat window, no?
Yeah, but can't see out here in Teams.
Okay. Maybe we can figure this out after the class. I'm not typing anything in the chat window right now, so it should not be an issue, at least for this class. We can figure out after class. Yeah.
Okay, sir. Okay,
Yeah.
sir. Thanks.
Yeah. Hari Om.
Hello, sir.
Yes. Hi.
Sir, can you provide the team code for this class? So then we will be able to access the chat and everything.
The Teams code was provided along with the link for the first class, no?
No,
That's how
sir.
I think you.
We joined via link only, so I don't think we have the code.
Oh, I see. I see. Okay. So, okay. How do I share that? I don't know. I've created a Teams and then I created the meeting for this first class. Okay. So what I will do is let me. And even if I want to share it, how do I get in touch with you guys? I don't know. I will post it on the class webpage. Uh, Okay, so I will probably post the Teams link on the class webpage. Only problem is I don't want random people outside of IISc joining. That's the reason I haven't posted anything. But I will post the Teams link on the class webpage once I figure out how to do it. I don't want to do it now in this time. Okay?
Okay,
I'll do it soon after the class. Okay?
okay. Thank you, sir.
All right. Yeah, yeah, yeah. Teams link. More questions? Yes, Rohit. Rohit, please unmute yourself.
Yeah, yes, good morning, sir.
Yeah, good morning.
Yes, sir. As you said, sir, like you will not touching the cryptography part and privacy security part.
Ah.
So, is it feasible to take cryptography course from the pool A?
Yes, you can take it.
So, sir, how it will like benefit us to like in this course?
So I can't explain everything today. You will see it as you go. Cryptography is, of course, going to teach you how to build the cryptography constructs. At the end of the day, in this course, we'll say, okay, use encryption here, use, MAC here, use digital signatures there. In that course, you'll learn the details of how these things are built, right? So in some sense, we'll be using those constructs as a black box. Uh, we will see, for example, when we touch the field of trusted computing, we'll be using hashes and hash chains and so on, which are very similar to the kind of data structure that you see on a blockchain today. We'll be covering all of these data structures, but at the end of the day, right, I mean, we are going to have to rely on some abstraction boundaries. I will be briefly introducing these constructs, but of course, if you want to learn how encryption algorithms these days are developed, you'll have to take the cryptography course. There's an entire science to it. We will not be actually covering that in that much detail. Rather, we'll just be using it as a black box. Just like, when you code, right, you use the printf function. Do you really understand how printf works? And do you really bother about how printf works when you use the printf statement in your program? Probably not, right? I mean, you just know the input-output functionality of printf and you proceed along with it. In exactly the same way, we'll be using the constructs from cryptography in sort of a black box fashion. If you really want to understand how they work, you can take the course that's being offered by Arpita and Chaya. Incidentally, that course is also being offered by this Karnataka State Center in Cybersecurity. So they'll also be recording their lectures and making it available via YouTube. So, even if you don't register in the course, that's an option. You can go and look up the relevant YouTube videos.
Okay, thank you so much, sir.
Yeah, Shashank. Shashank, please go ahead. Okay, I can't seem to hear Shashank. Likit, Hariom, can you please remove the hand raise?
Sir, good morning, sir.
Good morning.
Sir, can you give some in how to read or how to approach the research papers? I mean, like,
Go to the class webpage. Go to the class webpage. There is a paper on reading a paper. Okay. So there are multiple pointers I have given in the class webpage in the resources section that tell you how to read a paper. So you go read that. Starting with how to read a paper. Okay. So it's a paper on reading a paper, some meta aspect over there. That's the best way to sort of learn. And the best way to learn is osmosis. You read it. See, one way to swim is to just throw you into the pool and learn how to swim. And that's the way it is, right? I mean, most of you have probably never read a research paper. So you'll have to do it by reading and trying it out. That's the only way of reading a paper. But of course, there are some resources in the class webpage. You can go there and then figure it out.
Yes, sir.
Ankit?
Thank you, sir.
Yeah, Ankit.
Sir, good morning, sir.
Good morning.
Sir, do we need to have good coding skills to take this course?
Yes.
Okay.
Okay. Any other questions? Okay, so if there are no other questions, we can move on to the technical aspects of the course. Okay, so let me just share screen once again. Okay, so I'm going to give you like a 10,000-foot overview of what computer security is and the basic principles that outline the field. Uh, and essentially what we will see is that these principles keep coming back over and over during the course. So during the semester, as the semester progresses, I will sort of make sure I emphasize on these principles. And I will probably turn off my video right now because I am anyway sharing the screen. So let me just turn off the webcam and then start the course. Okay. So computer security is, as you may all at least loosely know, it's the study of weaknesses in systems and attacks against these kinds of weaknesses. So we will also be looking at how to defend against these kinds of attacks and methods to proactively protect data against various attacker models. Okay, so the question is, do we even know what a secure system is, right? And are we aware of real examples of secure systems, right? We are very often told that some system is secure, or that this system is not been attacked, so it is probably good to go. So what do we mean by a secure system, right? I mean, it's a system that is connected to the internet and running, let's say, the standard software stack that we are using today, which is maybe an email client, a web browser, and so on. Is that system generally considered to be secure? What about your smartphone? You're running apps from various sources, probably downloaded, hopefully from the Google Play Store. Is that a secure system, right? So what do we really mean by security, right? We have to understand and define that question first, and you will see that many a time it is a struggle just to define what we mean by security, and just the definition will give you an understanding of what you mean by security for that particular system. Okay, so here's an example that goes to show you how difficult it is to define an absolute notion of security. So this is what is called a cold boot attack. It was demonstrated around 12 years ago at this point, but it has extreme practical relevance even today. So this is a system, it's a laptop that has been switched off and it's not connected to the internet or anything like that. But the laptop was previously used, let's say, to browse some websites. Maybe it was used to log into your bank. Okay, so you've entered your credentials, your login and your password and so on. But you switched off the laptop when your banking session was still active. Okay, so the cookies and so on that were part of the banking session are probably still in the memory. But what do you expect when you turn off a computer system? You expect that at least all of the contents of what is there in memory have gone away. Okay, so what this shows you is that you can actually recover the contents of memory using this particular method that was called a cold boot attack. So what the attackers in this particular case did was that you get these cans of cold air. In fact, I think they contain cold nitrogen or something like that, that are used to clean keyboards, to remove dust from keyboards. So what they did was that they just removed the keyboard, exposed the memory chip, and then exposed the memory chip to these sub-zero temperatures. Okay, just immediately as soon as the laptop had been turned off. And your abstraction of memory is that the minute you turn off power to it, all of the contents of memory get zeroed out. So they showed that in fact that's not really the case, and this slide sort of gives you an intuition of what they were able to uncover. So let's say that you have a picture of Mona Lisa somewhere in memory. So what they showed was that if you spray the contents of memory, if you spray memory with this really cold air, then essentially the charge in these memory cells, it deteriorates a little bit slower than if you would just to do this at room temperature. So by just reading the charge in these memory cells, you can try to figure out the contents of memory. And what they showed, you can see the progression is, I think this progression was in 10-second or 30-second intervals, how the contents of memory degraded. So you can see after the first interval, you can still see some remnants of Mona Lisa. In the second interval, you can still see a little bit. In the third one, it's there, some black and white lines. You can see a vague outline. But the point is that this image of Mona Lisa still is there in memory, okay, for some time, even after the laptop is switched off, when you spray this really cold air on it. Okay, so what are the real world implications, right? Why do I care about stealing a picture of Mona Lisa? So I'm not really stealing it from the museum in Paris, right? So it really is worthless. But the point here is that your computer stores secret information often in memory. This could be saved passwords, your cookies with your bank, and so on, that if it's available to an attacker, the attacker can then go and replicate the session. So why is this important, this kind of cold boot attack? Are you going to give your laptop to an attacker and say, hey, spray cold nitrogen on it? Well, so the practical relevance of this attack comes from the fact that, what's the first security threat to smartphones? It is misplaced smartphones. So imagine that you leave your smartphone lying around and then somebody comes and the smartphone is still active, and then they go and do exactly the same attack on the smartphone and recover the contents from the memory. So you have lost all of your credentials from your active apps. And so that's the sort of real world implication of this cold boot attack. And it really makes you question what a secure system is, right? So this is probably the most secure kind of system that you can think about, which is that it's not connected to the internet, it's not really interacting with anybody, it's switched off, but still the the data that's available on it, and probably the disk over here is encrypted. The fact that the disk is encrypted does not matter because data still resides in the clear memory, right? Because programs have got to be able to act on them. So it shows you, that you really have to think hard about what you want to secure. Okay, so the basic components of any security course and any secure system are three goals, right? And not all systems aim to achieve all three goals. They go by a handy acronym, which is CIA. So confidentiality, integrity, and availability. So confidentiality is generally the goal of trying to keep secret things secret. Okay, so we have got some data that you want to protect from the attacker. You don't want the attacker to ever read the contents of this data in the clear. Then the goal of protecting that data from ever falling into the hands of the attacker is called confidentiality. Integrity means protecting the correctness of data, right? You never want data to be corrupted. So this is particularly true, for example, in bank databases and so on, where you never want the bank balances of people who have accounts in the bank to change, right? You never want an attacker to go and modify the bank balances. So that is integrity, right? Integrity means you want to be able to determine that the data that you have stored in your system is correct and has not been tampered with by an attacker. At the same time, there is another notion of integrity, which is origin integrity, which goes to speak about the identity of the person that is sort of doing the operation. That's called authentication, right? Whenever you get a connection from, let's say, Google, you want to make sure that, in fact, the claimed entity that you're connecting to is Google, okay? That it's not somebody else that's pretending to be Google. And of course, what happens if you fail to do such authentication? Well, you become the subject of things like phishing attacks. Okay, and the third aspect of security is availability, which means that whenever data should be available, whenever you want to access the data, it should be available. And there are threats to availability that are also possible. So, for example, denial of service attacks are a very popular kind of attack that compromise availability and make sure that data is not available when the attacker, when the good guy wants to go and access the data. Another really popular threat to availability these days is ransomware, right? So where somebody goes and downloads a piece of malware that goes and encrypts everything on disk, and when you want to go and access the data, it is no longer available because now everything is encrypted and you have to pay a ransom in order to access your clear text data. These are all threats to availability. Okay, so The goals of security, they are manifold, right? So you want to prevent the attack from ever happening. That's of course the ideal goal if you can prevent the attack from happening, but that may be too strong in some cases, in which case you might say that it's a good enough goal if you try to detect the attack, right? I mean, you really don't care about preventing the attack, but at least if the attack has happened, you want to be able to detect the attack. That's the next best goal. And the third best goal, if prevention and detection are not possible, either because it's too expensive to deploy it in practice, expensive in terms of cost or in terms of runtime performance of the defenses and so on, you at least want to be able to recover from a state of attack. Okay, so you want to be able to stop the attack and assess and repair the damage that the attacker has done. So these are sort of the spectrum of various choices that you as a defender have when you're trying to devise solutions to these kinds of attacks. Okay, so whenever we talk about security, we always have to understand what is it that we're trying to secure. Okay, so it is clearly not possible or meaningful to say that a system is secure, period. Okay, so you have to define what the assumptions you're making are, and the way of formalizing this is what is called a threat model. So a threat model is basically a set of assumptions that you're making about the power of the adversary or the power of the attacker, and you're trying to defend and you're trying to build a system that is going to be secure against these kinds of attackers. So concept of a secure system is always defined with respect to or modulo a threat model. Okay, so you can never have an absolute notion of security. A notion of security is always with respect to an implicit threat model, and it's in your best interest to make it explicit and make the threat model known so that no wrong assumptions are made about the security of your system. So there are various threat models that are known in practice. So for example, you might want to say that a system is supposed to be secure even if it is exposed to arbitrary network traffic. Okay, so you're exposing your system to an arbitrary attacker, maybe you're exposing certain ports, and despite this, you want your system to be secure. So that's called a network adversary, right? You want to be able to secure yourself even from arbitrary network adversaries. It's probably the strongest threat model. You might want to say that your system is probably you don't care about the network adversary, but you care about data at rest. Maybe you have a server on which you're storing some data, and you don't want you want to protect this data from physical access, right? So somebody comes and accesses the disk or steals the machine. You want to be able to make sure that the data there is still secure. And so that is the concept of a local attacker or a disconnected machine, where you still want to reason about the security of the system. So there are various threat models. I'm not going to do a comprehensive survey today, but rather, as we move along during the semester, as I cover various attacks and various defenses, I will always be talking about the threat model, which is the assumptions that you're making about the attacker. And if you are going to build a system and claim that it's secure, it's sufficient to make sure that it's secure with respect to that threat model, which means that you can prove that as long as the attacker is playing within the rules of that threat model, your defense is strong enough to defend against that attacker. Of course, the attacker might break the rules, might go outside of these assumptions, in which case your defense is not strong. You have to build a second layer of defense. And this is the way it goes, right? But at least when you make a threat model, you as a person who's writing a defense have a very clear set of assumptions on how to proceed to build your system. Okay, so a very related notion is that of a trusted computing base, which is the set of hardware and software components that you trust whenever you're building a secure system, right? So you want to ensure that everything that's part of the trusted computing base is behaving as advertised, that there are no attackers sitting within the trusted computing base or the TCB, and all of the assumptions that you make about your system are modulo this assumption that the TCB is secure. If the TCB is compromised, you can no longer guarantee the security of the system. So to give you a sort of understanding of what this TCB is, let us just look at a real computer system, right? When you are, let's say, browsing on the web, or checking your email, or let's say visiting your bank website or things like that, what do you trust to make sure that your banking session is secure? Well, you trust your web browser is implemented correctly, that the web browser does not have a malicious actor sitting inside. So your web browser is sitting on top of an operating system. You're trusting that the operating system is going to be working correctly. And underneath the operating system, you have the hardware, and you're expecting that the hardware will work correctly, right? So there's this layer of software that you're trusting, layer of software as well as hardware that you're trusting in order to make sure that everything is working correctly. And that forms the trusted computing base for that particular activity, which is that of visiting your banking website and then making a secure transaction over there. Now, anything over here that's compromised will compromise the integrity of the entire banking session. So, for example, if you have a browser that you've configured properly, or let's say you're not following best practices with your browser, or let's say you fail to ensure that you're using HTTPS or the bank is using HTTPS, your banking session is compromised. If there is malicious software sitting within the operating system, it can observe everything that's happening within the web browser process. And again, your banking session is compromised. Of course, we never think about hardware being compromised, but it's certainly possible, right? So how is hardware manufactured these days? Well, you think companies like Intel and AMD and Nvidia actually have engineers sitting and soldering transistors to each other? Uh, no, right? I mean, the way that hardware is manufactured is just like software, right? So software engineers sit and compose modules in VHDL or Verilog or some such hardware description languages, and all of these things pass through a compiler. And at the end of the day, the output of the compiler is something called RTL, which is then burned into silicon at a fabrication facility, God knows where, maybe in China, right? And who knows, right? Maybe this fabrication facility is actually inserting a backdoor. This is called a Trojan, right? To enter into the hardware and compromise or read everything that's happening. So what I'm telling you is not far from reality. In fact, there are attacks that have been reported. Okay, and these attacks on Trojan hardware are extremely important. Probably not in your day-to-day life, but rather in military settings where the military is actually deploying sensors on the ground to go and monitor the enemy's activities. You really want to make sure that at this point the hardware is actually trustworthy. So, uh, you know, whenever we think about our trusted computing base, we have to always think about these assumptions about what is it that we are assuming secure. All right, so whenever we talk about a secure system, you should also remind me to tell you what a trusted computing base of that system is. Again, there is no one definition over here. It all depends upon which system you're trying to secure. During the course, we'll be talking about malicious software at the application layer. We'll be talking about malicious software within the operating system, and we'll also be talking about malicious software within the compute infrastructure. For example, within the compute infrastructure that underlies the cloud. So in each one of these cases, the trusted computing base is going to be different. So ideally speaking, the smaller the trusted computing base, the better it is, obviously. The lesser you have to rely on, yeah, in order for your system to be correct and secure, the better it is. Okay. All right. So I just covered this slide. Let me move on to the next slide. Okay. So the third notion I want to tell you about is that of policies and mechanisms. So in this course, we'll be talking about both, right? So we have to understand that it's very important, not just for this computer security course, but rather any systems course that you take, operating systems, architecture, networks, whatever course you take, you will encounter these notions of policies and mechanisms. And it's very important to understand the difference between a policy and a mechanism and to have these things as two separate notions in your mind and always approach the design of your system with these two things as separate entities. So a policy is essentially an entity that says what is and what is not allowed. Okay, so it tells you what is correct and what is not correct. It tells you what is secure and what is not secure. Okay, whereas a mechanism is a set of tools or tricks that you use in order to enforce this policy. Okay, so it is the set of entities that you use to enforce this policy. Let me just give you a very simple example, right? How do you protect the physical security of your house? Well, you put a lock on the door, right? So the lock in this particular case is the mechanism that is protecting the physical security of your house. If you and the when you decide to lock your house is a question of policy. you might decide to leave your house unlocked all the time except at night or when you're traveling out of station. So that's your policy, right? And the more you lock your house, of course, it is better in terms of protecting the assets that are inside the house. If you don't lock your house, available to the person on the street for longer. Okay, so that's the policy. The mechanism, of course, is the lock that you're using to guard the house. Now, if you go and buy a 10 rupee lock and you use that to lock your house, obviously anybody can come and pick it up with a safety pin, right? They'll come and open it and enter your house. So if you really, really want a good lock, you go and buy one of the really costly locks, sort of the Mercedes Benz of locks, and then you use that. Of course, your house is going to be more secure than the 10 rupee lock. Okay, so that's the mechanism. Now we clearly, in order for a good security system, you need both a good mechanism as well as a good policy. It's not enough to, you might keep your house locked all the time with a 10 rupee lock, but that's not really going to protect your house, right? Anybody can come and take the lock. At the same time, you can have the best lock, but you decide not to lock the house, nobody can help you. Okay, so you need to have good policy as well as good mechanism in order to achieve your security goals. Okay, all right. So that's what that is. Policies and mechanisms. I've covered this in the slide. Let me move on to the next slide. Okay, so now what I'm going to do in the next sort of, I think I have around 25 minutes. I'm going to cover 8 security design principles. You will see that these design principles feature over and over again during this course. And you might not appreciate all of these principles right now, but they are discussed as part of the first reading for this course. And I will at least give you an overview. Okay, so you're familiar with the terms, and when we come back to these terms later in the semester, I will explain them in context. Okay, so the first principle that we are going to have to sort of have to obey while building secure systems is the principle of least privilege. Okay, so what this says is that a subject should be given only those privileges that it's necessary to complete its task, no more, no less. Of course, if you give less, the application is not going to work, and if you give more, you're too permissive. So when I say subject here, so this term is very commonly used in security. Subject can mean user, it can mean program, it can mean application, whatever it is. Okay, so the principle of least privilege states that you should only give a subject only those privileges that are necessary to complete its task. So the best example that I can give here, that of least privilege, is I hope at least the majority of you over here are Android users, or if not, you're at least familiar with the way that Android works. When you download your applications from the Play Store, you get a permission screen, or your application is going to ask for permissions to, let's say, use the camera, access your contacts, access the network, and so on. Right. So at least over here, in terms of, it's giving you the ability to say yes or no when you are accepting the app, but you're setting up a certain sandbox over here. If you download, let's say, an application and give it access to the camera, it can access the camera, but it can probably not access anything else. Likewise, when you download an application, maybe it's an application to, let's say, do spell checking of documents, right? Why does this application need camera? And so if you say that the application should not access camera, or you verify that the permission screen it is not asking for access to the camera, you have at least ensured that the application is not going to have access to the camera. So here you are doing the least privilege checking to make sure that the application only has access to what it needs in order to accomplish its task. The second principle is that of fail-safe defaults, which means that in a secure system, the default action should be to deny access. If you don't know what to do, or if your policy is ambiguous with respect to what to do in a particular case, your default action should be to deny access. And if the action fails, the system essentially is as secure as when the action began. You have not really compromised anything. And so a popular notion over here, the best way to describe this is this notion of blacklists and whitelists, or what is increasingly being called deny lists and allow lists. So you'll see over here that a whitelist or an allow list is basically a list of people who is allowed to do a certain activity. This way of doing things is a fail-safe default, okay? Which means that if you're not on the whitelist or the allow list, you're not allowed to do the particular operation, okay? As opposed to a security system that uses blacklists. A blacklist is basically a list of bad operations or bad actors. So whenever you see them, you must disallow them from doing things. Okay. So what happens if you see somebody who is not on the blacklist? Uh, Generally speaking, in a blacklist-based system, that person is allowed to do the operation. And so that's an example of a fail open system, which is a bad design principle in security. Okay. So so that's the idea behind whitelist and blacklist. So the most common example of blacklists is, for example, your antivirus systems that you would purchase from most commercial vendors and install in your system. So the way that they detect viruses or any sort of malware is that they compare the malware against a database of known signatures of malicious software. And if the system, if what you just downloaded does not match any one of those signatures, they declare that software to be safe to use. Now, obviously, we know from practice and from news articles that we read in the real world that anti-malware systems are not perfect, and this is exactly the reason why they're not perfect. Because if they don't match anything in their in the list of signatures, the software is allowed to actually execute. So that's an example of a blacklist-based system. Nevertheless, these systems have their place in the real world. Okay, so the next principle is rather vague, but you will begin to appreciate this as you build a complex software system. It is a principle of economy of mechanism, which means that in any real software system, you want to try to keep it as simple as possible. Your design decision should not be complex. Okay, and the simple reason, the simple rationale behind this is that simpler means that less can go wrong and that you can reason about the correctness of the system. And so what this means is that when you're designing a system, you should have clean, minimal interfaces, and this applies particularly to TCB design. So we will see this principle as we go along. I don't have a good example that I can offer you over here to illustrate this principle in practice. Okay, so the next principle is that of complete mediation. The principle of complete mediation states that you should check every access to let's say some secure data. Let's say you want to protect access to data. You should check every access to that data. Okay, and this is called complete mediation, which means that every access to the data, no matter what path and code you're using to access that data, should contain the check whether you're allowed to access the data. Okay, so this principle is sort of important for security. If you find a code path where you're not performing this check, that can generally be exploited as a loophole. Okay, to give you an example of the principle of complete mediation, and how it's violated in the real world for the sake of efficiency, you should go and write a simple program in Unix. Let me see if I have the example. I don't have it here, but you should go and write a simple program in Unix to actually open a file and then go read the file. You open the file with read permissions, and then let's say you read the file in that process. Let's say you have another shell that's open in parallel where you're also trying to read the same file. Okay, so that shell initially has access to read the file, and in the process of, let's say, opening this in the first shell you're trying to open and then read, let's say you turn off or you disable read access to that file to this program as the program is running. Can you still continue to access the file? Okay, so in a Unix system, you'll find that you can continue to access the file. You will still be able to read the file, even though, let's say, you've turned off permission to read the file in a parallel shell using the chmod command. And so this shows that on a real Unix system, the principle of complete mediation may often be violated. And we'll see this. We'll see that this is in fact a trick called capabilities that is used in Unix with file pointers. And when we come to that topic, we'll talk about complete mediation in much more detail. So the fifth principle is that of the principle of open design, which means that the security of your system should never depend upon the secrecy of the design or the implementation of your system. Okay, so if any aspect of your system depends upon keeping the design secret from the attacker or the adversary, that system is going to be broken very soon. Okay, so this is popularly misunderstood to mean that source code should be public. That's not the case. In fact, you will find that for attackers, assembly code is often as good as real source code. What This means, what this particular principle means is that you should never try to achieve security through obscurity. Okay, the aspects of the design that you're using to secure your system should be available to the attacker, and your system should remain secure despite that. Okay, so in particular, right, when you're designing, for example, a cryptographic system, the encryption and the decryption algorithm should be available to the attacker, and the encryption and the decryption algorithm should work despite the algorithms being available to the attacker. The only secret information that, for example, you're allowed to have there are the cryptographic keys that the encryption and the decryption algorithms will use in a particular invocation of the encryption or decryption algorithm. Okay, so that's what the principle of open design means. The sixth principle is that of separation of privilege, which means that generally speaking, you should not have one giant system that is endowed with all the privileges of your system. And whenever you want to grant access to, let's say, a particular secure resource, you need to be able to separate the privileges between multiple parties. Again, this is a rather this principle you might not see applied in day-to-day practice, but when it comes when the system is applied to when this principle is applied to a system that we will encounter in class, I will certainly make sure I talk about this principle and illustrate it with respect to that particular system. Okay, the next principle is that of least common mechanism, which essentially states that mechanisms should not be shared between various components of your system, because whenever you have mechanisms that are shared, information can flow across shared channels. Okay, and as a result, you will see that if this principle is violated, you can have things like covert channels and side channels that result. And we will talk about covert and side channels in the system during this course. In fact, we will be talking about the meltdown and Spectre attacks that became quite popular around 2 years ago, and we'll see how, for example, a failure to adhere to this mechanism can result in these kinds of channels. Okay, and the last principle, which is probably the principle that is the least precise to state, but the most important in practice, is that of psychological acceptability, which essentially states that a secure system cannot be secure, or a security system cannot be secure if it is very, very hard to use. Okay, so often you find that security gets in the way, right? How many times have you downloaded an Android app from the Play Store and just clicked yes to the permission screen because you cannot be bothered to check all the permissions that the application is asking for, right? So this is an example where, if the user is not well educated about what is going on, then security essentially becomes, the human becomes the weakest point in the link. You will find, for example, that phishing attacks are also an example that sort of illustrate that the human is often the weakest link in the chain, right? So psychological acceptability means that when you're designing a secure system, you should make sure that the system is also usable to the end users, right? So another popular example here is that you will find many, many websites, when you go and try to set up a password, they come up with obscure rules, right? Okay, you should have 3 capital letters, 2 special characters, 3 numbers, and so on. And you might actually end up creating such a password. But guess what? How will you remember that password? You'll probably write it down somewhere, right? And somebody gets access to that sheet, then your security is gone. There's a very good anecdote here, that actually talks about Richard Feynman, the really famous Nobel Prize winning physicist. When he was designing the nuclear bomb as part of the Manhattan Project during World War II in Los Alamos National Labs, he actually compromised the security of a lot of people who had top secret clearance. How did he do it? Well, he would just go to their secretary's desk and open the drawer, and right there in the drawer, because the secretaries needed to have access to the top officials' email, because they would send emails on their behalf, they would actually have a post-it note over there with all the passwords. And lo and behold, he just goes and opens the drawer. He's able to get top secret clearance to all of the top generals who have all of the access to the designs of the nuclear bomb. Okay, so there you go. Humans are the weakest link in the chain. Okay, So that's it for today, right? The key points is that these 8 principles you will see sort of coming into action over and over again, a subset of these principles at least, in every system that we study in this course. And so whenever we talk about a particular design principle, I will come back and re-emphasize one of these design principles. But these 8 principles you will see in action again and again during this course. Okay, and so with that, let me just conclude today's course, today's lecture. Let me again open the floor for questions before I finish the class. We have another 10 minutes for questions. Aditya has a question. Please go ahead.
Yeah, sir. So the fourth principle that was about like checking every access to something, you mentioned that on Unix,
yes,
it is once opened, like it doesn't check again. Were we
yes.
referring to the original Unix or were we referring to Unix-based systems?
You can even
Like,
try Linux today. You go write the following program, right? Go open a file with read access, and you know, perhaps it can be a large file. So you do a read in a tight loop. Okay, make sure that the read takes around 10 to 30 seconds to complete, and make sure that this program has read access. Simultaneously, in another shell, go ahead and remove read access to this particular program. Okay, so do chmod 000 of that file. Which means that even if you try to open that file, you will get a permission error. But you will find that the program that's already opened this file will be allowed to continue reading. Okay. Why so? Because every time you read this file, you're not actually performing the permission check. The permission check is performed once during the open call. Once the open call has succeeded and it's given the file descriptor to the read system call, read system call will be able to continue reading. That's an example where you don't do checks every time you read. So in principle, it's a violation of complete mediation, but there's good reason for that in order to maintain the efficiency of the system in the real world. And you will also see that it's a slightly different way of thinking about security. It's not access control list, but rather when we talk about capabilities and access control lists in this course, we will actually talk about this in much more detail. Okay.
thank you.
All right. Shashank, you have a question.
Yes, sir. Am I audible?
Yes.
Hello. Yeah, sir. So sorry, previously there was an issue. Yeah, my question is about the 7th point, which was the least common mechanism.
Yes.
Is it by any chance related to code reusability? Like we should not use if you are using code, reusing the codes, it is a potential vulnerability. By any chance, it means that?
Well, yes and no, right? I mean, these days, code reuse is not something that we can avoid, right? All of us use libraries. The principle of least common mechanism here actually refers to the mechanisms that you're using within the TCB, right? I'm talking about things like virtual machines and so on over here. So what this refers to is essentially the least common mechanism within the TCB, where you want to share as little code as possible between these two components in order to obtain security. Easier said than done, right? I mean, these principles are there in the real world for a reason, but they are violated very often in practice. As you rightly identified, you reuse code all of the time, which means that if you have a vulnerable library, right? I mean, you have to patch the library and make sure that all systems that are using it are either patched or you use things like dynamic linking, in which case you pick up the latest version of the library.
Yes. Okay. Then this dynamic shared libraries are also a potential vulnerability.
Of course they are, right? I mean, so dynamic shared libraries, you have to patch them, but the thing is that unless you have any running programs with them, the next time you run the program, it's going to pick up the latest patched version of the library. That's how dynamic linking works.
Correct. Yeah. And sir, there was a previous question that I was not able to ask. I was going through some course material and I found some assembly code. So do you advise to know assembly code also? Yeah, get to know assembly code also for this course?
Yes. So, in fact, it's a little bit premature, but next lecture we'll be starting a discussion on memory errors. I will be talking about some basics of assembly code, but you will be expected to pick up a little yourself. Nothing too complicated, just some basics, some simple instructions, push, pop, basic add instructions, and so on. Of course, the papers that we cover will also talk about a little bit of assembly. But yes, it's going to be very low level, at least for the first homework and the first few papers, because all of these things are going to be working at the assembly language level of abstraction.
Okay, sir. Thank you.
Yeah.
Hello, sir. This is regarding the fifth design principle.
Yeah.
So it says security should not depend on secrecy of design or implementation. So,
Right.
like in general, security means maintaining secrecy, right? Like I might not have understood the principle correctly, or
Okay, so again, it's a question of what you want to protect and the system that is protecting it. So, of course, you want to protect things like, for example, your Aadhaar number or your credit card number, right? That is the data that you want to protect. Now, you have certain code in your system that is actually trying to protect access to it. So, what are these things that are protecting access to it? So, for example, in your browser, right? If you save your passwords using the browser safe password facility, well, the passwords are all there in your browser, right? But what prevents other people from going and accessing these saved passwords? So, for example, let's say you visit a random website. What prevents that website from going and looking at your browser's local storage and looking up the passwords? Well, it is the code in the browser and the certain principles that the browser is using to ensure that web-based attackers don't have access to the local system. Now, that is the principle that the browser is using to protect access to your saved passwords. But the browser source code is available to the attacker, right? It should be available to the attacker. The fact that you're protecting these saved passwords within your browser should not depend upon the secrecy of the browser source code or a secret design in the browser. Rather, the source code of the browser should be available to the attacker, yet the strength of the security principles, the strength of the security architecture of the system should still save your passwords from falling into the hands of the attacker. That's what I mean by open design. When I talk about open design, I mean the design of your security system should be available to the attacker, right? Not the data that you're trying to protect. The design of your security system, the mechanisms and the policies should be available to the attacker, and the system should still be secure despite this information being available to the attacker. Is that clear?
yes, sir. Now it's clear.
Okay. Gokulnath.
Sir, but wouldn't obscurity add another layer of security by making it things more difficult for the attacker?
It could, but it's just a matter of time. And as they say, it just takes one clever attacker to defeat a system, right? So if you've got an obscure system that's really hard to reverse engineer, but you've got one attacker who sort of breaks into it, that's all it takes, right? Now that's not to say that you cannot have randomness in every run of your system, or you cannot make it harder for the attacker to sort of come and uh, take over your system. But obscurity should not be your single line of defense, right? Your entire basis for security should not be obscurity. Of course, you can add obscurity or keeping the design principle, the design of your system secret, and so on as one layer of your defense. But it should probably be the least significant layer, right? It should not be the factor that determines the security of your entire system. In practice, and it's been shown over and over and over again, people who keep design decisions secret and keep and base their security on the fact that something was obscured from the attacker, these systems are broken sooner rather than later because, as they say, you should never underestimate the power of the attacker.
Thank you, sir.
Yeah, yeah. Any further questions? Devraju again. Go ahead.
Sir, if you design any system, is it mandatory that that system design should follow all the 8 principles?
No, certainly not, right? And you will find that very often you will have to sacrifice some of these principles, the interest of cost or efficiency, and at least you should be clear about that, and you should document it. Make sure that you're at least able to reason about why you're doing these things. No single system will follow these principles. In fact, we'll find that these principles are better written on paper than implemented on a real system. Very often you will find that. But they exist for a reason, and at least you should try to, follow these principles wherever you can.
So they are used as a reference.
They're used as a reference. They are probably not always followed in practice for various reasons, and we will see this.
Okay, thank you.
Yeah. Any Manu? Go ahead.
If we are doing any research on this computer security side, whether we are trying to develop a new security algorithm or some new mechanism which implements all these 8 policies.
Well, research is a far way off from what you have seen today. You will hopefully get a flavor of that when as we progress through the course. Again, even the first part of the course is just going to be an introduction. If you're interested in research on this topic, you will have to really pick a particular topic and then start reading more and more papers. It's too early to sort of say generalize to research from this first lecture alone. These are just the basic foundational principles of the field.
Okay. Okay, sir. Thank you.
I think with that we are out of time. My action item at the end of today's lecture is to try to find the Teams link for this and post it on the class webpage. I will do that. You can, in the interest of questions being shared with everyone, I would recommend that you post any questions that you have to the chat window once I enable it, rather than sending me email, because that will save me effort also. One more question, Ashish, and then we will close the class.
Hi sir, can you provide us the PPTs of the lecture along with the recordings?
Go to the class webpage. It's already all there. Not just today's
Oh,
PPT, but the PPT for the full semester. Everything is there.
okay,
Only
okay,
the
sir.
recordings I will be uploading as and when I record it.
Yes.
Yeah. Okay. All right. Well, thank you. That's it for today. Next class will be on Wednesday at the same time.